called the birthday problem. And so in probability, we've talked about several different types of probability situations you need to know about. This is one that we can't walk away from, our content and our course and everything we've talked about, from the probability of darts to the probability of casino card games, to the probability of dice, to the probability behind let's make a deal, where you choose the door that's the prize and the other doors are zonks, conditional probability, all of it. We have to talk the birthday problem because this one is so surprising. In the birthday problem, we can guarantee, with leap years for consideration, leap years, February 29th, every 4 years, under most situations, there is a couple stipulations or not, you look that up, that's your job. But if you put 367 people in a room, guarantee 2 of them are going to share a birthday. With 100% accuracy, we know it. How many people do you have to have in a room to guarantee half, right? Half of the people in the room the wrong way to think about it, of a collection of people, a group, what is the size of the group so that there's a 50-50 chance, or better than 50-50 chance, that 2 people will share a birthday? And we don't care what day of the year, just as long as they share a birthday. How many randomly chosen people are needed before the probability is greater than 50% that at least 2 of them have the same birthday? That's how the book said it. Which do you like better, my way or the book's way? Be honest. So the probability of any day times the probability that it's a match. This is saying no, you pick the day, I'll pick the match. Let's see what that probability is. It's going to be 366 out of 366. The probability of a match, 1 out of 366. So the chance that you have a day, you have a second person together, and the chance that they share the same birthday, just those 2 people, is actually really, really unlikely. The 366 over 366 reduces to 1. So this is just 1 out of 366. And by the process of complement, the probability that any 2 people just don't match in their birthday is 365 out of 366. Right? The idea being 100% the total of matching, not matching. You just add the fractions and you get this one. Okay, cool. So let's carry on. What if there's 3 people? So that's any person matching. So you pick the day or the person, they just tell you your birthday. The probability that another person is not gonna match them is gonna be 365 out of 366, right? That's this fraction, the probability of no matches. And then times the probability of no matches. So 364, none of them match. And if you multiply all of that out, hey Siri, what's 366 times 365 times 364?
It's 48,626,760.
I'm not writing that down. Okay, let's go to the calculator on this one. Let's go 365 divided by 366 times 364 divided by 366. By the way, I'm not writing down 36 times 30 or divided by 366. I will, and I'm going to delete it. I skipped this calculation because that's going to reduce to 1, so it's not even necessary to calculate out. Now they give us the fraction. I'm going to press Control Enter to get a decimal. There is a 99% chance that those 3 people will not match. It is less than 100 though. It is less than 100. In fact, let's just compare this to the original, 365 divided by 366. So the probability of 2 people matching, not matching, went down to the probability that 3 people won't have a match. It's a slightly smaller probability. 99.7% down to 99.2%. And if the probability is going to continue to drop, I would say at some point, it's going to be below 50%. And if the probability is below 50%, then we can conclude that the rest of it is there's got to be some people matching with their birthdays in that scenario. So if we keep on going, of 4 people, that'd be 366, 365, 364, 363 divided by 366 to the 4th. So calculator time, swing that up, oh, goodness gracious. Pull this down to center in. Sorry if the screen went wonky on you there. So 366 times 365 times 364 times 363 divided by 366 to the fourth power. Decimal point, please. Control Enter. 98% chance. 98.3% chance. And so perhaps the best way to let the calculator function for us is to just keep multiplying the numerator denominator by a fraction. So I'm going to go up. Boom, boom. And I'm going to go times 362 divided by 366. I need to fix this to be a decimal. I know it's wrong. This is 5. So then this is going to be 4. Or 6, I mean. This is 6. And then this is 7. And then this is 8. This is 9. 358 over 366. This is 10. That percentage is now starting to come down by a lot. This is 11. Oh, gosh. I need to go up. Times this. There we go. This is 12. This is 13. This is 14 people in the room. What's the probability that none of them share a birthday? We're now at a 23% chance that 13 people, 2 of them have to share a birthday. 23% chance is pretty decent. And I say 23 because it's the rest of this non-matching percentage to get up to the total. This is 14 people. If there are 14 people in a room, then what's the chance that none of them have a matching birthday? 74, 75%. What if there are 15 people in a room? What's the chance that none of them match? What if there are 16 people in a room? What's the chance that none of them match? What if there are 17 people in a room? What's the chance that none of them match? What if there are 18 people in a room? Or 19 people in a room? Whoa, that's almost 50 right there. We're at 19. What if there are 20 people in a room, and the chance that 20 people, there is no match between 20 people, it's only 55%. We're close to half. 21 people. What if there are 21 people in a room? What's the chance that none of them match? And so every time that I put a different number, it's the calendar days that we have left that we could consider. So there are 345 other days that are just not the same as the first 20. 52.5% chance that 21 people will not share a birthday in common. Okay, let's put 22 people in the room. 22 people in the room, there it is. If you have 22 people in a room, you have a better than 50% chance that 2 of them are going to have the same birthday of the entire year, leap years included. Let's put that down. How many people is that? It is 20. Whoa. It is 22 people. Usually when this question is worded or asked, or you consider it as a piece of trivia, some sort of like math club knowledge bowl type question, or just like a trick to ask people unsuspecting math facts, they would say, ooh, half of 366 is around 190, or 180. So there must be you have to have 180 people in the room. No, probability doesn't work that way. That's linear thinking. Probability works on an exponential plane, man. And so therefore, when you talk about adding up, not conditional, but compound probabilities, we got to think about the opposite of what we're looking for and compound that. And ultimately, that exponential change produces a really small number within a classroom. Go into your next class and ask, hey, who here shares birthdays? And I'm going to tell you, more than 50% of the time, there will be people in that class that share birthdays. And you don't know them, they don't know each other, but that's the odds of it all. And here's the mathematics of it. Thank you for watching. Oh my gosh, this has been the entire geometry sequence. I appreciate you being here for the entire journey, and I hope to see you in other episodes as we continue our learning. Have a good one.